Hello, today we will try to understand something about free convection. Convection is a mode of heat transfer wherein the heat transfer takes place due to the bulk motion of fluid. In free convection, this bulk motion of the fluid is an effect of the change in density of fluid on being heating or cooling. In a normal case where a flat plate is there at a higher temperature Ts, what happens and why this sort of thing happens that the fluid that is near the surface gets heated up, and when it gets heated up it usually expands, and due to expansion the density decreases, so this fluid it moves upward, and due to this upward motion some void is created here, and instantaneously some other fluid that is not here and that is usually at a lower temperature than this air rushes down to this place and fills this gap. So a bulk motion happens, and due to that bulk motion heat transfer is enhanced. In nature also, when we are near a beach or where some coastal areas, what happens that during days the sun is very hot because that is usually these areas are near equator. The land heats up and the nearby air also heats up, it rushes upward, and instantaneously or simultaneously the cool air that is nearby rushes to the place, creating a soothing breeze that is very calming, and the calming reason is because that it our body generates some sort of heat and it helps us to cool down. So that is why this is an example in the nature that happens. But for our mechanical analysis or engineering analysis, what we do, we keep things simple. So for because here the motion is in the horizontal or vertical direction, in the upward direction. So what happens? We take a flat plate which is vertical, and the liquid that usually is close to this surface, if the surface is at a higher temperature than the fluid, it gets heated up and it starts moving upward. Rest remaining area is taken to be quiescent, which means that it is undisturbed, and because of the decrease in the density of this fluid moves up, and this motion, this bulk motion, is responsible for the cooling effect or the heat transfer which is happening. In older times when AC and all this heat transfer things were not so advanced, how people used to have a cool environment and a cool ambience. The walls of the building were very thick, so heat sun rays didn't the heat transfer was slowed down, and the height of the buildings was very high. In old movies and old places and old monuments, you can see the height of the buildings is very high. Indoor heights are very high. There is a reason, because as much higher the buildings are there, or as much the system is high, this motion the density change will have a larger place to play, and the natural convection will be more effective. So if people are sitting on the ground floor or at the bottom, so what happens, because so much height is there, so natural convection although will happen in a smaller room, if the height would be like this in small cubicle sort of thing, then also natural convection would have happened. But because here the height is very high, so natural convection is more effective, so cooling happens in a better way, and without any AC you are getting a better ambience inside. So this was the technology of the olden days. No compressor, nothing is required. Simply using the property of fluid, we are generating some cooled environment. So the mechanism behind this, there are two cases. The first case is where the bottom temperature is hot and the top temperature or and the top surface is cool. So the density at the bottom will be very low because the fluid has expanded, and top the density is high. So this is something like heavier thing is on the top and light thing is at the bottom. Heavy thing is at the top and light thing is at the bottom. So this is sort of an unstable thing. Usually what happens is the heavier thing is at the bottom. So this is an unstable sort of situation, and this stays unstable unless and until this temperature or this density drops to a certain value corresponding to a higher temperature, that the buoyant force, the buoyant force and buoyant force, what buoyant force is, what is it, is the weight, it is the force acting on the fluid which is equivalent to the fluid displaced. So this area, this the buoyant force, when it is so high that it is able to go up, until that point it will stay in this situation only. So this is an unstable equilibrium sort of thing. On another example is where the bottom place is cooled and the hot and the top plate is hot. Here what will happen, the density, you see density here is less on the top. So this is sort of a hydrostatic sort of arrangement here. That heavy thing is at the bottom, that is usually stable thing. So here what will happen, there no bulk motion will take place. Only maybe through some conductions, through some molecular diffusion, the heat will be transferred. But here, because things are unstable, some sort of cells will be developed, some cold fluid will come down, hot fluid will go up. These kind of things will happen once the instability starts. Now, there are two examples. One is when there let's assume this is a tube or something which is heated up. This is a rod. It is inside, perpendicular inside and coming outside. So what happens if the whole area is stationary, nothing is moving? So density will decrease and it will make some sort of a plume. This is sort of a boundary layer example. And another example is, for example, you see, if you are in your garden and you have your pipe and you start watering plants, water usually drops down because of gravity. But if a heated liquid is uh, coming out of this tube, because of its less density, this liquid will start to go up. This sort of setting is known as buoyant jet. These are two examples in natural convection. And why this is happening? This is happening because it is related to something known as coefficient of volume expansion or expansivity, which is denoted by beta. What is the essence of this thing? Why the density is reducing? Why the air is getting lighter? Because once it is heated, the volume starts to expand. Like in solids, when you expand it, it expands in one direction equal to alpha times the length. So that sort of thing, it starts to expand, and when this expansion takes place, the density is has to reduce, and it is quantified by this term beta, and it is defined at a constant pressure. And so this the unit is Kelvin inverse, or inverse degree Celsius. And if you calculate this for an ideal gas, it will turn out to be 1 upon T. So usually what you think, a fluid will always, when you heat something, it will expand. But there is one very peculiar thing, and that is known as water. Water, at some point of time, at some temperature range, near 4, water has a maximum density, 4. So if you are talking about water in this area, in this region, then okay, it's fine. When you increase temperature, when temperature is increased, the volume also increases. So this thing is a positive. This is has a positive value. But below here, when water, the temperature of water is less than 4 degrees Celsius, what will happen? This is decreasing. So this will be negative. And if you see this in terms of beta, so every typical fluid has a positive beta value. But for water, what happens here, near about zero, it starts to become negative. The beta value is negative there. So if in a normal setting, if this plate was cold or is cold, the liquid will cool down, it will come down. These two are cold liquid, and fluid will come here, normal any typical fluid, and because it's getting cooled, it will become hot, it will go down. But this can be water in case of heating. If water is around 3 degrees Celsius, this water, it is water around 3 degrees Celsius, and we start to heat it. Temperature here, although it's not the case, but if temperature is high, it will show the same thing. So water, there is a temperature where things are exactly different, and this happens for no other fluid but only water, as far as I know till now. Now, when very important thing, see, when we are talking about force convection, there what is happening, the flow field is already determined. You know what is the flow field. There will be a plate, or there will be a any arrangement and forcefully by some prime mover or some external agency, you will create a velocity field and you will know what the velocity field is there. And that will means you know the parameters of the momentum equation. We need not go into such detail, but just hang along. And what happens because of this thing? The thermal field is generated, the boundary layer thickness and how boundary layer thickness is changing. So there is a dependence. There is a one-sided dependence. One we must know the velocity field, and thus after some calculation or something, we will get the thermal field, how the thermal things are behaving. And Prandtl number is involved there. But in case of natural convection, what is the problem or what is the scenario? Because because the field is generated or happens due to change in density. Density is the change in density is the moving factor. So there is a dependence on this temperature field of this density, and density terms comes in multiple location in these equations. So what happens? There is a cyclic dependence. The how the velocity will be there, then the thermal field will change, and then when the thermal field will change, it will in turn change the velocity field. That is how it happens in nature instantaneously. You need not to calculate these things. This is called a means cyclic relation. But what happens when you are doing simulation and when you are trying to understand or when you are trying to model these kind of things? This is very tricky. At sometimes you can make okay, I will consider only one time the dependence, or I will go for twice the dependence. But for calculation, we cannot do these kind of things. So what Bosniak, there was a person known as Bosniak, he gave an approximation to analytically solve these problem, and what he did, he removed the bottom dependency. What happens that this density function, this density, it's not that important in some places, but it is when the body forces, only the major part or the very important part, which is the driving force, is the body force. So this thing is taken as a constant in some place, but it is taken as a variable in the uh, body force. So body force is the cause of this motion. So at body force, which because density is a function of temperature, so we take the density as temperature in case of the body forces, and this works very nicely in it only doesn't work when the temperature difference is too high, and in some other special cases, but usually for every practical application on earth, it works very nicely, beautifully. It is known as Bosniak approximation. So Newton's law of cooling is same as it works everywhere whenever there is convection. So if Q is the rate of heat transfer, it is proportional to the area, it is proportional to the temperature difference. So there must be a constant, and this constant is known as convective heat transfer coefficient. In case of natural convection, it will be convective heat transfer coefficient for natural convection. So, and there is an equivalence because at surface, when convection takes place at the surface where the y is equal to 0, this line, this red line at surface, there is no bulk motion. So it's sort of heat is coming here and some equivalence, it is going, convection is happening here, but at some point of time here this conduction is happening. So these has to be equated. One way of calculating this, on the way we will calculate the convective heat transfer coefficient, is by equating these two things. This is Fourier's law, and this is the Newton's law of cooling. And now we will, when we equate this, we will get this heat transfer coefficient. And what we need, this can be found from properties, this can be measured by thermocouple. This thing is the profile of temperature at the surface of the layer or the boundary, that we need to calculate somehow, or we will see. So in major setting, four type of things are possible. One that I already told, forced convection, other is natural convection, one is boiling, and another is condensation. Why I am telling this? Because I want to give you a comparison of how effective these things are. Free convection is almost the least effective thing. Forced convection, there is a problem, but it's little bit more effective. It needs a prime mover. There is a prime mover that is required somehow. And in phase change or in phase change or boiling or condensation, the heat transfer coefficient is very, very high, or maximum. But the advantage of natural convection is that you don't need any external agency or any external force. If you design the system properly, it will work just fine. You need not do anything. The non-dimensional numbers that are related to natural convection. First is the Grashof number. Grashof number is the ratio of buoyancy force to the viscous force. If the Grashof number is too high, then it means okay that the buoyancy forces are predominant and they are in action. So this is, and you see this L cube. This L is has a power raised to 3. This is very important. This shows that the thing that I initially told, that the system, as much as the system is high, because it will turn out that this Nusselt number for natural convection is a function of Grashof number and Prandtl number, and the higher this length means 3 times power is there. The system, if the system is having a much higher height, then it would be more effective. So setting second thing is the Prandtl number, and it's the ratio of molecular diffusion of momentum to the momentum diffusion of heat. Then there is Rayleigh number. Rayleigh number is the governing number for the transition in natural convection. It is the multiplication of Grashof number and Prandtl number. And for a critical amount of value, like just like Reynolds number in forced convection, we get to know okay if the flow is laminar or if it's turbulent. Nusselt number is the ratio of the convective heat transfer coefficient to the conductive heat transfer, and this is the prime target usually, which efficiency finally leads us to this H value. So the target in any convective heat transfer problem is to find the Nusselt number for this situation, so that we can find this convective heat transfer. Here, in case of natural convection, as I already told, I'm very sorry, Grashof number is not there. But Grashof number is there. Grashof number is there. Prandtl number uh, is there. So it's not wrong. It's correct. So Rayleigh number is there and Prandtl number, because Grashof number is included in Rayleigh number. So in natural convection, Nusselt number is a function of Rayleigh number and Prandtl number. So what happens if the Rayleigh number is around 10 to the power 9 or greater than 10 to the power 9? We will say, okay, the transition has taken place for all practical purposes. If it's below, Reynolds number doesn't work in this natural convection thing. Here, Rayleigh number works. Rayleigh number is less than 10 to the power 9, then it's laminar. If it's greater than 10 to the power 9, then it's turbulent. These are the correlations that are used for natural convection. We have vertical flat space, we have inclined flat face, horizontal heating phase upwards, heating phase downwards, horizontal cylinders and spheres. And you see there is only Rayleigh number and Prandtl number, or only Rayleigh number or Rayleigh number Prandtl number. So this essentially means that is a function of Rayleigh number and Prandtl number. And there are ranges where these things works. You see this Rayleigh number is from 10 to the power minus 1 to 0.1 to 10 to the power 10, means it works in laminar and this region. It works in both region, and we will find out that for this problem we will use this correlation only. This is very established correlation. And sometimes what happens, you see there is no vertical cylinder in this case. You see no geometry is there that can work for a vertical cylinder. So sometimes what we do, we make certain assumption. We assume that okay, we will cut this cylinder and we shall assume a flat plate which is vertical. So that kind of assumptions and things which are justified can be done and are usually done in practice. One very important thing when we are seeing that Prandtl number is required and other values are required, at what temperature will you find these thermophysical properties? So the thing that is used in practice is that we take the average of the surface and the fluid and the temperature of bulk fluid, and that is known as film temperature. And these properties are determined on the film temperature of the system. Applications, there are some very although they are natural application, but some very nice application like solar updrift tower. So what happens in a huge area in desert or some places where it's very hot or solar energy is very concentrated and is in abundance, what they do, they make a very high tower. See, the length is very high. In any place where natural convection is working, length is a very important factor in the vertical direction, in the direction opposite or in the direction of the gravitational field. That is very important. Everything is working here due to gravity only. If gravity is in space, it won't work. So we need some length. So a very tall tower is there, and this area heat is incident in by sun, and this area here it gets heated up. It's all get heated up, and because it needs to go up, it will go up in this tower, and as it goes up the speed increases, and there are small turbines over here, small not small, there are turbines over here, and these turbines help generate electricity. So this is one application for this natural convection, although it can be argued that it's not natural convection, but it's sort of an application that is relevant, that seems relevant. This is a picture of such of a plant in Spain. You see there, this is transparent, these things are transparent below, and you see the height of this. This is humongous. It's so high. Another thing I've heard that in thermal power, in nuclear power plant, it is required. I went into little detail. So what is there? Usually, what happens that previously it was used as a passive, because you see when power plant breakdowns. You see in Japan also there was a breakdown in power plant. So that is a very catastrophic situation. And at that point of time, electricity is not there and anything is not there, but density will decrease and the gravity is always there. So in case in as it is used as a natural convection process is used as a fail safe, and it's called as a passive fail safe. The word is passive. Passive way it is used. But nowadays, Bark is working on a Bhabha Atomic Research Center that is working on some sort of a new thermal power plant that is advanced heavy water reactor, and this is indeed advanced because it is using natural convection for both active and as a active in normal operation situations and in the case of a failure. So see here, this is the core. This is the area where all the heat is being generated, and there are two loops there. One loop is this failure loop. I might be little wrong, but there are two loops. Loop one and there is loop two. There are two loops. One is for active removal of heat, another is for the passive removal in case of failure. And the pressure inside, let's say P in is the pressure inside and P out is the pressure outside. So P in is lesser than P out. So in case of any failure or any leakage, the outer liquid goes inside the core, not the inner liquid going will come out of the core. So it reduces the contamination. So in case any failure happens, the hot liquid will rise up, and this height is quite high. And I'll show this. This is quite high. You see, this is also a diagram, and this portion, this the region where the fuel rods are there, that is known as Canandria vessel. And this looks very small on this diagram, but you will get an idea. See, if Calendria, okay, you see, this is installation of a Calendria vessel, and now you get an idea how high this structure will be. If water is here in this area, at least one, two, three, four Calendria vessels can come up, and you see how much high this is. This is the height of a average person here, maybe 1 meter or something. So lot of height is there. The liquid is not even air. It is water or heavy water or deuterium or something. So the temperature very nice sort of cooling can happen, and it's possible, and it is something that is happening now. This is one of the very systematic application of natural convection that I found. And one very interesting thing, that these kind of things, everything will not work if gravity is not there, because you can say that okay, density driven, but why is it density driven? It is density driven because there is some gravity field available, and if gravity field is not there, it will not work. See, if on earth this candle is burning in this shape, is because the lighter air is moving upward, but when you go into space, it will not burn like this. So gravity density, it is density driven, but gravity is also required in because to get it working. So experimental method, how we can measure this convective heat transfer coefficient experimentally. There is an assumption that is steady state. We need a steady state situation. That that is, if some amount of heat is coming, the same amount of heat is going out, and the internal energy is almost fixed, and that means that the temperature of the system is not rising. So what happens if we can get an amount of heat? We artificially can generate some amount of heat electrically, just Vi, power is equal to Vi, power is equal to I square RT, that kind of thing. And then we can apply, or some way fluid is moving outside, some way it's moving. So then we can equate these two things, that the power that is coming, it's going outside, and using these equivalents we can find the convective heat transfer coefficient for natural convection also. So in this case, we need a very high, we need a vertical tube, and in a vertical tube, what we will do, uh, we will we have some length and some diameter, and this is solid in this case. On this, and it has some outer surface area, that is pi dl. We have a thermocouple for ambient temperature outside, and we have some thermocouples on the surface as well. Now what we'll do, we will start to heat this solid cylinder, and when it's get heated up, and this is an enclosure, so that outside air does not affect our system. So liquid will get heat up, and slowly it will start moving upward, so some bulk motion will start. And when then this bulk motion will start, so after some time, after steady state conditions are achieved, we will get these things. This is the ambient temperature, this will be the average surface temperature, this is the heat transfer. So we can get this convective heat transfer experimentally for our natural convection, and in this case the system will be vertical. Now lab demonstration, let's see.
This is our experimental setup for calculation of convective heat transfer for natural convection. Here we have a vertical solid pipe, which is heated from inside, and outside on the surface there are 7 thermocouples, and there is one thermocouple which is at the back, which is used to calculate or record the atmospheric temperature. This is our control panel for this experiment. Here we will see the current reading, here we will see the voltage reading, here the various temperatures will be indicated. When we switch this setup on, there is no current in the heating coil inside. Now when we will use this dimmer stat, the current in the heating loop will increase. We will slowly take it to a specific value. Now to calculate or to see the various temperatures inside, for example, this will give T8, the ambient temperature, 25.6 degrees Celsius, and these are the readings on the outer surface of this cylinder. For this experiment we only need one reading, and after some time these temperature readings will change and take a steady value, and using those values we will calculate the convective heat transfer coefficient.
Now the calculation part. So what data will be given? We have the dia of the pipe, and we have the length of the pipe, and gravitation relation we have. These values will be found from some table, from thermophysical property table. These things will be measured, this voltage, current, and the temperature. Only these three values will be given. The rest will have to be calculated. It's not that difficult. So calculation, for experimental calculation, what has to be done? There will be average temperature, there is ambient temperature, and as I have already told, we will just put them in this equation, and we will get the experimental heat transfer coefficient. And those datas we can have this, for Rayleigh number, these parameters have been clubbed in this thermophysical table, so it's very easy. We do not to take values differently from different places. So how do we theoretically calculate this thing? First thing, we need the Nusselt number. For Nusselt number, we can arrange it in this form so that we get the convective transfer coefficient. The thermal conductivity of air we require, we will get it at the film temperature. And for force convection, the Nusselt number is a function of Rayleigh number and Prandtl number that we know. And what Prandtl number? We will find that Prandtl number from those tables at film temperature again. Rayleigh number, as I already showed you, this thing is already there. At the film temperature, this part is clubbed together for ease. Simply we need to take temperature difference and height raised to the power 3. We will get the Rayleigh number. And which relation to use, that I already explained, that vertical plate will work, so that Churchill and Chu correlation will work, and using this correlation you can put Rayleigh number here, Prandtl number here, and we will get this Nusselt number, and that's it. When we will put this Nusselt number here, we will put this diameter over there, and we will put this uh, heat transfer thermal conductivity of fluid here, then we will get the convective heat transfer coefficient theoretical value. One small correction here. The Nusselt number for free convection, here we will not use this dia, because when you will open this as a sheet, and otherwise also here, as I've already told, the height of the system is the characteristic dimension. So instead the theoretical heat transfer coefficient will be Nusselt number into thermal conductivity of fluid divided by this length L, the length L. So what are the deliverables for this experiment? The experimental heat transfer coefficient and the theoretical heat transfer coefficient. Thank you.